So today we are starting a new chapter, as I said, not included in the exam, which is magnetic susceptibility.
Is this for the quiz or not?
30 seconds ago I said that not.
Okay, I'm sorry, this was...
Okay, usually denoted by high. And what does it mean? Someone knows here? Susceptibility?
1 plus
Not the, what is the meaning of the word? Or what is the procedure that we are doing in order to...
I think it's relevant for linear materials, and it is some sort of a ratio between the magnetic field and the magnetic moment in something, right?
Exactly. What susceptibility means is we turn on a weak magnetic field and see what is the response of the system to this magnetic field. There's a lot of different susceptibilities in physics, could be electric, anything that you turn on a field and ask what is the response is susceptibility, as long as the field that you turn on is relatively weak. So here we're talking about the case where we take a material and turn on a weak magnetic field and ask what is the response of the material to this magnetic field. And actually, for most materials, will have two very different responses, which both are connected with the electrons in this material. And we'll see that because of two different properties of the electron, we'll see two kinds of responses. Okay, so basically we have people divide, or physicists divide, the response of magnetic materials into three categories. Ferromagnetic, paramagnetic, and diamagnetic. So a ferromagnet is what you in the daily life call a magnet. It's a material that has a constant magnetic moment, and due to the magnetic field, it may change its direction or get ordered. A good example for that is iron. Iron has a permanent magnetic moment. Sometimes, due to disorder, it's pointing in all directions. And when we take a weak magnetic field, all of them get aligned, and you get a permanent magnet there. Meaning if you turn off the magnetic field, you still have magnetic moment. I don't know how many of you as kids took an iron pin, moved it on another permanent magnet and saw that it becomes magnetized. That's a ferromagnet. This we won't discuss in the coming lecture. Paramagnet is you turn on a weak magnetic field and you get a magnetic response in the direction of the magnetic field. Diamagnet is the opposite. You get a response in the opposite direction of the magnetic field. Okay, so that's just categorizing the types of response that we can get. So a ferromagnet is a permanent magnet. Paramagnet, magnetic in the direction of the field. And diamagnetic opposite. In both cases, the paramagnetic and diamagnetic, you shut down the magnetic field. No more permanent magnetic field. You get zero magnetic dipole of the material. Okay. I won't go into magnetic response that come from the nucleus of the ions or anything like that. I'm looking only on the response that comes from the electrons in the material, and it's from free electrons. So, which itinerate, which means free electrons. Now, there are two different physical effects that can drive a magnetic response from the electrons. Why? Because there are two different origins of a magnetic dipole in electrons. The first is the spin of the electron. And this is known as Zeeman effect. I mean, the electron has spin, and you probably have seen that the energy of a spin in a magnetic field is equal to Have you seen this term?
Yeah.
Probably you have seen it some. This is the spin of the electron. This is the magnetic field. G0 is almost 2, and corrections to it are very interesting because they're relativistic effects, and UB is permittability, another constant. Okay, so we'll see how this fact influences the magnetic response of the material. And the second one an electron has charge, right? It moves. Again, true. Moving charge responds to a magnetic field. So we have a second origin of a magnetic response, which is the orbital effect. And we'll see exactly how this influences the results. Okay, let's go back to the definition of chi, and chi is equal where m is the magnetic moment of the material, and through a thermodynamical connection which is the second derivative of the free energy. Okay. Let's look on the first mechanism. Okay, so Zeeman, sometimes also called Pauli. So, simplest thing in the world, number of electrons up minus number of electrons down, and minus because all the peculiarities with minuses that we have in electromagnetism. Okay, so it's just counting the number of electrons with spin up compared to the number of electrons with spin down. Okay, let's consider what can happen when we are putting a magnetic field on our system. Okay, with no magnetic field, I'll fill up half of the states will spin up, half of the states will spin down, and in this situation, m will be equal 0. Okay, then you can ask me, why don't I take this spin and pull it here? And then the answer is simple. This costs more energy by delta. Delta is a level spacing here. Okay? Just doesn't make sense. Now, you could ask me, and what happens if you have an odd number of electrons? So you have a very small magnetic moment that is random in direction, and if you actually for very small nanosystems it could be measured. For regular large macroscopic metals or things like that, unimportant. Okay, so this doesn't happen because it costs you energy, and m is equal 0. Actually, it's interesting that in atomic physics you can get a permanent magnetic field, which is known as Hund's effect. From where does that stem? So this is a sidebar. Hund effect occurs in atoms where you have several degenerate states. So let's say I have 4 states which are degenerate. Usually we have 2 states, spin up and spin down. Here we have 4. Why can it happen? We know that in atoms we can have degenerate states. Now here there's no difference between this case and this case, right? They cost the same energy, unlike in this case. So how does the system choose between those 2 states? It's because in atomic physics, usually we neglect another term, which is interactions between electrons. Now, if the 2 the 2 electrons sit on the same state, they have maximum overlap of their wave function. Costs a lot of interaction energy. If there are 2 separate states, then there's no there is a smaller interaction energy. So this state is larger energy than this state. Well, actually, let's write down the states. If this is state 1 and this is state 2, this is state 1 and this is state 2. To put both of them spin up and spin down on state 1 costs more energy than putting them both on state 1. So that's the Hund effect, explains a permanent magnetic moment in an atom. Okay, but that's atomic physics. Okay, so what happens here when we put a magnetic field? So this is for B equals 0. And what happens then? Okay, let's look on the Zeeman term, which guys which are in the direction of the field pay less energy. Okay, I assume that B not equals 0 and in the up direction. So these guys went down in energy. On the other hand, those which are in the opposite direction go up in energy. Okay, so at the end of the day, I fill up according to the lowest energy that is open before me, right? So, if the field is above some value, and let me exaggerate a bit, make a stronger symmetry here. So in this case, I would prefer fill my electrons more in the direction of the field and less in the direction opposite the field. Meaning I create a magnetic moment in the system. Now you could tell me that for a field approaching zero you don't see any effect because the movement of the levels are below delta, the separation between the levels. But if you're thinking on a very large system, this delta goes to zero, so even a magnetic field which is infinitesimal gives you a response. Again, in nanosystems...
Like, could each atom have more than one energy level?
Excuse me?
Because each atom have more than one energy level and have a bunch of different atoms?
We have 10 to the 23 atoms.
So even if only one or two spins are on each atom, there's so many atoms.
There's enough of them to create a response even for fields that goes to zero. If you want to be more mathematically precise, you would say that the order of taking the limits there should be first take the system to infinity, then take the field to zero. These types of games, as I said, become important when you are talking about very small systems where it can have an effect. Or for example, in molecules or atoms, where you have a small number of electrons. Okay. So let's write it down mathematically, since we understand the physics behind it. Okay, so instead of writing down the number of states, the density of states at a given energy, I can write down the density of states for each spin direction, which will be just because each state there could be either populated by a spin up or a spin down. So I have half of the states at a given energy which accept spin up electrons and half of them which accept spin down. And this is, of course, when B is equal 0. On the other hand, when B is not equal 0, okay? All it says is that when I'm putting in an electron, it will be shifted either by minus mu b or by plus mu b. Why I'm writing mu b and not what happened to the g and all that's written here? S G is 2, S for a spin half is half, 2 times half is 1, so we are left with just mu b. Okay. epsilon. Let's leave this and continue here. What did I do here? I took each one of these terms and wrote, since the magnetic field is very weak, that's susceptibility. And the same here. So I just wrote a Taylor expansion and took the first term because B is small and put it in here and got the number of electrons in each direction. Minus plus because here is minus, here is plus. Now, in order to determine mu, of course, I need that the number of electrons for mu. What's nice about this expression?
Derivative in integral?
Yes, but even nicer is you have a simple dependence on B. When you go and calculate the susceptibility, you don't care about this term. And all you have to do is half mu times this integral. So, just one minus the other. And what did I do here? In any integral, when I move the derivative from one part of the integral to the other, it is of course integration by parts. Right. Check that the second term has to fall off, equal to 0. Okay, for t equals 0, life is really easy because and what is the derivative of the Fermi function at 0 temperature? To remind you, the Fermi function at 0 temperature just completely filled up till Fermi energy and 0 beyond it. Derivative of such a thing is a delta function. In this case, a minus delta function because of the directions. I have here a minus. So n in this case depends only on the density of states at the Fermi energy. Another example of the importance of the density of states at Fermi energy, because at the end of the day, how many electrons I can move from up to down depends on the number of electrons at the Fermi energy. Above it, it's not relevant. Below it, they can't move. So the susceptibility and this is, of course, paramagnetic response. Well, to know that it's paramagnetic, I didn't need this whole calculation. Just if the spins align in the direction of the magnetic field means that the magnetic field creates a magnetic moment in the direction of the field. Therefore, it's paramagnetic. Okay, so Zeeman effect is usually simple. What will happen if I have a finite temperature? Okay, we have again corrections of order T around EF. Sommerfeld, I won't go into the details because we did something like that, and it doesn't change dramatically the paramagnetic response. Okay. Now let's go to the orbital effect. And in this case, I'll treat the electrons as free electrons. And for simplicity, I'll think about two-dimensional electrons. Why two-dimensional? First, because it's simpler. Second, because surprisingly, the effect that we'll discuss here about two-dimensional electrons is the basis of two Nobel Prizes that were given in the 80s for the quantum Hall effect. And it's cute that a relatively, it's not completely simple, but a relatively simple calculation, it gives effects that were discovered only 40 years ago, or less than 40 years ago. Now you can stop me and say, sorry, why do we discuss a completely hypothetical case of two-dimensional electrons when our life is carried on in a three-dimensional environment? How do you get two-dimensional electrons? Actually, it turns out that in the experiment, we can actually see two-dimensional systems, which the way to create them experimentally is not very different than what we have seen for the p-n junction. In principle, so it's known as the two-dimensional electron gases, and on a very simplistic level, you take two semiconductors which have a different gap. That's enough to create it. So let's see. So we have one system and the other system. Okay? You put them together. We know nowadays to grow, let's say, gallium arsenide and all kinds of hybrid structures like that. You are creating a crystal of one till a point, and then start growing another type of material on top of it. That's done nowadays readily. So in the usual case, okay, we have mu somewhere in between, nothing interesting happens. Now let's consider the case that we add donors somewhere here. We have here some donors. What will happen? Okay, that's large energy. This is lower energy. The electrons will start to populate this region, right? And here we'll get positive ionized donors. We have seen it already for the p-n junction. Would all of them move here? No, because you are creating an electric potential. So they will accumulate on the boundary. And you can create a very thin boundary of electrons here, which is essentially two-dimensional. So that's how you create a two-dimensional electron gas in the laboratory. And that became like the workhorse of a lot of quantum studies in semiconductors and generally all kinds of materials. That's to create a two-dimensional electron gas on such surfaces. Let's say any one of you have heard about quantum dots. That's how you start, and then do a bit other games with it, and you can create here a region, a very small region that can accumulate only a few tens of electrons in a potential well. A few tens of electrons in a potential well is actually an atom. So you can go and create an atom, it's not an atom, it's electrons in a potential, with levels according to what you decide. How you build it, meaning, let's say, for example, it can emit photons in certain wavelengths that you determine. There are other ways to build it, like very small metallic clusters, but this is one of the easiest cases. And then you have a whole playground to create all kinds of properties that you're interested in. Okay, so although two-dimensional sounds exotic, go into any laboratory nowadays that does semiconductors, they do it routinely. Okay, so how do we calculate the response to a magnetic field? Well, let's take the simplest case. We have already considered what is the effect of lattices on these games, the tight binding, nearly free electron. But for our purpose here, it's enough to go to the simplest model, which is
Nearly free electron?
Forget the nearly. Free electrons. As usual in physics, if you want to see the main effect, you start from the simplest model that gives you, and then you see if the fact that you have a lattice really changes much. But for this effect, a lot of the physics you can pull out just from the simple free electron. So I'm writing down the Hamiltonian. Okay, so P square. And the previous part was in Ashcroft. This is a part that doesn't appear in Ashcroft. It's more modern, and at the time that Ashcroft was written, it wasn't thought to be very relevant. Okay. So, what is A?
The vector potential?
The vector potential you have seen in analytic mechanics. That's the way you write the Hamiltonian if you have a magnetic field system. So A is the vector potential. Let's just put the magnetic field perpendicular to the two-dimensional system. Why perpendicular? Because if we put it in plane, we don't have any orbital effect. Think about how a magnetic field has influence. Think about Lorentz or the change in current due to change in a magnetic field. When does it, on what does it depend? Back to high school physics.
Change in flux.
Right, and if I have in plane on a two-dimensional system, what is the flux? Zero. Just nothing. You have to be perpendicular to see some flux. Okay, so I'm taking a perpendicular field and taking the corresponding magnetic vector potential. Why? You can see curl of A is equal B. Now you could stop me and say, excuse me, but you could have chosen different A's, right? What's it called for in the system?
Calibration?
No, it has a name that becomes very important in physics further on.
Degree of freedom?
Look. Gauge invariance. I can choose different gauges, different representations of A's that nevertheless gives you the same value of curl A. Anything which is a div of A doesn't come into effect here. So, why did I choose a certain structure of the vector? Well, we will see that this will turn out to be convenient, and the only thing that we have to worry about that our final results shouldn't depend on the choice of A. And we'll see it once we get to a result. But for now, we're using a specific gauge, and we'll see what it gives us. Okay. So let's rewrite our Hamiltonian. Why? Because AX and AZ are equal 0. So they are not in the game. Or in the y direction, I have to write down AY. Because it's not 0. So we get a non-symmetric Hamiltonian, but that's expected. We chose an unsymmetric A. So let's explicitly write the Hamiltonian. Okay, let's look on what's happening here. In the z direction and in the y direction, we don't have other explicit dependence on the coordinate except for the derivatives. On the other hand, and in the x direction, we have here some explicit dependence on x. So we'll guess a solution. Which we say, well, we know that if we have only derivatives of x and only derivatives of z and only derivatives of y, usually the solution is of the form e to the power ikx, iky or ikz. And we don't know what happens with phi x. That we will calculate and see if we get a consistent answer.
Y direction. When you have a second order differential equation, like something with a second derivative and with the first derivative?
No, let's see what happens and see whether it works. Okay. double derivative on second derivative of z gives you k z squared. We don't know what to say about the derivative in x. Here we have one derivative takes down iky, minus this term, and the ikx, ikzz and ikyy drop out of the equation.
Where?
This, of course, squared. Right.
Where did the second h bar come in the? Where is h bar squared?
Here?
Oh, because you add the square, right?
And this is, of course, h bar. Okay. Let's rewrite this a bit. All I did here is divided by this term. And got x freestanding. Okay. Looks a bit frightening, but actually this is an equation that you have solved in quantum mechanics. Why? This is a constant, right? Nothing to gain. Okay, this is a term of the second derivative in x. This is actually a potential.
This is harmonic quantum oscillator.
It's a harmonic oscillator. If I call this x0 and this omega 0 square up to h bars, sorry, up to half m, we're exactly solving the problem of a harmonic oscillator. Extremely surprising. We started from a problem that, on the face of it, has nothing to do with a harmonic oscillator, and ended up with an equation for a harmonic oscillator. Why is it? What is the physics behind it? Well, it's not a miracle. Let's think about an electron in a magnetic field. What do you remember from Lorentz forces? What is the motion that it does?
Circular.
Does just a circular motion around the magnetic field if it has velocity in the z direction, so it does a spiral. So in the xy plane, at the end of the day, it just does a circle, which if you think about it after quantization, it's just a harmonic oscillator. Because if you think about representation of amplitude, it's also a sine and cosine, so it's a circle. So, although it's a bit surprising, it makes sense. So, let me rewrite it. Where omega f0 is just defined here. So without further calculation, I just go back to the solution of a harmonic oscillator. I know that for the energy x0 doesn't play any role. And I get okay. That's from this part. Since mu b is equal I can rewrite it as Okay. So, you could have stopped me in the calculation and tell me, you started from talking about 2D systems, but you wrote a solution that is a 3D solution, right? Kx, ky, kz. There was nothing that was two-dimensional. And indeed, we solved it also for a three-dimensional free electron. This term makes life a bit harder, and we'll treat it in the next lecture. For two-dimensional, what is equal kz? 0. I have only one quantum state that sits there in the z direction. So I can rewrite this is of course plus. So what are the available states? Differently. And so on and so forth. Okay, how many electrons can sit in each state? Infinite. And I'll prove it in the next lecture. Infinite or proportional to n, the number of electrons in the system, of free electrons in each atomic level. But we'll go into it. This is known as and the fact that you have very discrete quantization in the levels of two-dimensional systems is perhaps one of the most basic features of modern quantum materials. Now, since some of you have an exam that starts at 2, we will stop here and go into the details of this in the next lecture. So those of you who take the exam now at 2 o'clock in my room in the Resnick building 207. For you, those of you who don't know on what I'm talking, it's not relevant.
רק שאלה קטנה.